Okay. Next, let me cover the very simple case of simple regression. When we say simple regression, that means there's only one predictor of the response variable. And here, when we talk about Bayesian linear regression models, the response variable is a observed continuous random variable. Okay, continuous random variable. Okay. What about a case in which there's no covariate? Okay, so let us begin with this very special case, this observable continuous response variable without covariates. Okay, without covariates. Well, we have random variable, right? Yi, okay, random variable yi, and given its population parameter mu, that is its mean, and here, we assume all these random variables, right? Draw from different, let's say, from different individuals. They're independent, identically distributed, and follow this normal distribution, and they share the same mean, that is mu, and same variance, sigma square. So mu here is something to be estimated. That's without any covariance, right? And in this case, let's assume sigma square is given or fixed. What we're going to do, okay? Then we can use the probability density function given in the previous slide to set up the likelihood. And here, we can assume a prior for this mean, right? And we say, well, it follows a normal distribution with a mean of theta and variance tau square. We can also view sigma, right? The standard deviation. It turns out to be, sigma square is much easier to handle. But let's say sigma as a parameter to be estimated. Okay, so again, we have this array of random variables yi given mu, but we have additional parameter sigma to be estimated, and follows a normal distribution with mean of mu and variance of sigma square. Okay, so we see, well, again, mu follows a normal distribution with its mean set to theta and standard deviation to be tau square. So that's the prior for mu. What about sigma square? Well, sigma square here, I just kind of vaguely say, well, it follows some prior probability density function, but we have to guarantee that this random variable only takes on values, positive values, because sigma square is a has to be a positive number. So we have kind of a couple options. For example, exponential distribution, which we will use in the simple regression case. And also we can assume gamma or inverse gamma distribution, etc. Okay, so once we assume these priors, and we also assume the likelihood to follow normal distribution, right? What we can do, well, we can just toss them into this MC machinery and then crunch out the posterior distribution. Okay. So now let's build regression model for this simple linear regression with one covariate, right? So let's say we have array of data, from unit analysis. In this case, could be individuals, could be countries, could be counties, right? But for each case or unit analysis, we collect two pieces of information. One is, y, one is x. So for the first case, we have y1 and x1. For the second case, we have y2 and x2. And for the end case, we have yn and xn. And here we assume y, the conditional y, follows a normal distribution. Note that here, my focus, our focus here is the conditional y. Equivalently, the focus can be the error term. And later, I'm going to show you in the Bayesian multiple regression case. Okay, so what's different from previous example or slide is that here we assume mu I, that is parameter, varies across cases, right? The parameter varies, right? Varies. Still, we assume this conditional normal distribution has a variance of sigma square. But why it varies? Well, because we impose a structure for this parameter mu I. We assume, well, it is equal to beta 0, that is the intercept, right? Parameter plus beta 1 and xi, okay, and xi. Okay, xi could be x1, x2 to xn, right? So because xi varies, of course, mu I also varies. The likelihood, okay, here is as follows, right? Here we have a product sign that is pi, okay, pi. Why it is product sign? Because for every single case, we assume a conditional normal distribution, right? Conditional normal distribution. Conditional normal distribution. And this is the mean here. This is the mean here. Okay, so the random variable, okay, minus its mean, and then square that and divide it by 2 sigma square within this exponential function, okay, etc. So if you check the probability density function that I laid out in one of the first few slides, you will see they're almost identical, but expressed in different ways because for the random variable and for the mean, I use different symbols and different terms. The additional symbol here is this product sign. Why? Because here we assume IID. That is, we assume all these cases, they're what? All these random variables here, we're talking about either the error term, equivalently the conditional y. They're independent and identically distributed. Okay, that means the likelihood of observing the data is a product of individual probability density function. Okay, so that is the likelihood. That is the likelihood. The next step is to specify the priors for slopes. Here, I also call beta 0 as slope. This is slope for a unit vector and beta 1. Well, a common prior for beta 0 is normal. So here for beta 0, I say, well, it follows a normal distribution with a mean of theta 0 and variance nu square beta 1. Similarly, right? But different, hyperparameters. We call, theta 0, nu 0, theta 1, nu 1 hyperparameters because they're parameters of the parameters to be estimated. And we can tune these parameters, hyperparameters, to match our prior understanding of beta 0 and beta 1. In a lot of cases, we assume not informative priors. That is, usually we say 0. And then for nu square, we give a very large number, to assume having no prior knowledge about these, parameters. Now, how about to specify the prior for the error variance, parameter sigma square? Well, so this is a variance sigma square, and standard deviation should be called sigma, right? And in this case, to satisfy the condition that sigma square is a positive number, we say, well, how about it follows a exponential distribution with its parameter lambda. Lambda is called rate or inverse scale parameter, and it is used in a lot of parametric models. For example, survival models, and another example would be Poisson regression models, right? When we get into those models, I can talk more about this distribution. But in this case, if we assume sigma square follows a exponential distribution, then expectation of sigma square is equal to 1 over lambda, and the variance, okay, the variance of sigma square is equal to 1 over lambda square, and that would imply the standard deviation of sigma square is equal to 1 over lambda, equivalent to the mean of sigma square. And if you know the basics about exponential distribution, we know that that's called equidispersion assumption, or property. Okay, so after I feed the priors, okay, then what we can do, we can turn to MC. Sometimes you can imagine that as a black box or a machinery, right? Toss those into the machinery, both likelihood and prior, then it's going to crunch out posterior distribution. And after it crunches out posterior distribution, what we can do, we can summarize the posterior distribution from different angles, right? We can get the mean, get the standard deviation, get the median, and get credible intervals, etc.